We're going to continue on here, chapter 7, going backwards. And we're going to talk about thermodynamics a little bit here, more about energy, which they really should do first semester, but they don't here. And then we'll go back and pick up the rest of thermodynamics. So we're going to talk about in this chapter, as it mentions there, energy. So let's get into that. So when we talk about thermodynamics, one of the main things that we look at when we're dealing with thermodynamics is the idea of a system and really its surroundings. So your system in a lot of cases is like your test tube, your beaker, whatever you may be doing the experiment in. And the rest of everything else is basically the surroundings. And in this particular case, we're going to talk about really energy and the flow of energy or heat from the system to the surroundings, or really even the surroundings back to the system. So we're going to have this sort of flow of energy occurring really in both directions. Now, when we talk about systems, there's really three types of systems that we deal with. We have an open system, and an open system pretty much can exchange energy and mass with the surroundings. So that would be like an open beaker. It just kind of take stuff out and put stuff in, and also can exchange energy with the surroundings. A closed system will transfer energy, but not mass. So you put like a stopper on your flask, then you can't take stuff out and you still have that energy flow. And we also have an isolated system where there's really no transfer of mass or energy in it. And in this case here, again, an open system, we could take stuff in and out. We also have that flow of heat and energy in and out. Put a stopper or something on there. Again, going to stop that sort of exchange of mass, but could still do that. In an isolated system, again, pretty much everybody's just inside, really no exchange of anything basically occurring. Now, when we talk about energy, energy is really the capacity to do work or to produce some type of change. And energy can be measured as the work done or the force times the distance. There's different types of energy. There's chemical energy. That's the energy, for example, there's energy stored within bonds, within atoms. So, for example, if you were to break a bond, that would be a endothermic process. You have to put heat and energy in to do so. Everybody gains some energy and they kind of wiggle away from each other and the bond breaks. If you want to actually make a bond, that also requires actually energy to be released in that case, which is exothermic, because everybody has a lot of energy. When they release the energy, they slow down and allows them basically to come together to make that bond, as opposed to when you already have a bond, you add energy to it and they wiggle away from each other and they're able to basically break away from one another. There is potential energy, which is the energy due to the position. The classic potential energy example, the big giant boulder on the tip of the hill there that's going to fall. It has a certain amount of energy due to its position. It could then perhaps come over the hill and convert into some kinetic energy, right? As we come down the hill, that's the energy of motion. Then it's going to flatten whoever's underneath there. Hopefully nobody's underneath there. It will also transfer some energy to whoever was underneath there, and also the cement ground there as well. So the law of conservation of energy is that energy can neither be created nor destroyed, but it can be transformed from one form to the next. Again, in this case of our example here, a certain amount of potential energy transformed to kinetic energy. And again, as it hits, is going to transfer some of that energy, obviously, to whatever is underneath it. And we think of energy as sort of this nice, perfect transfer of energy. So the idea here is if somebody loses a certain amount of energy, somebody else should gain the exact same amount of energy. So, for example, if a reaction gives off 5 kilojoules of energy, the surrounding air should pick up that 5 kilojoules of energy. So this nice sort of perfect sort of transfer of energy that sort of happens. Now, thermodynamics, like energy that we're looking at in really this chapter, and we'll cover the rest of sort of thermodynamics in the next chapter. But thermodynamics is really the study, in this case, of the interconversion of heat and other kinds of energy. And a lot of what we look at is in the next chapter in terms of thermodynamics. Thank you. We look at the idea of whether or not a reaction will take place. And a lot of that is sometimes dependent on energy and energy being sort of dispersed from one state to the next. Now, there's a lot of properties that are determined really by the state alone. And that is basically what are referred to as state functions. State functions does not matter really the path you take to get there. There's kind of only two things that are really important when you're talking about a state function, and that is kind of where you start and where you finish, basically. So if we look at these two hikers, for example, here, hiker in the red here took the scenic route around the mountain, took some pictures, some selfies as he was coming up the mountain. The blue guy here took the more direct route up the mountain. In terms of their potential energy, they basically have the same potential energy as they both started and ended in the same sort of spots, basically. And things like energy, pressure, volume, temperature, those are all state functions. Really, the only two important things is where you start and where you finish. And that's why a lot of times we take, for example, our final minus our initial in terms of like volume and energy and pressure along the way. Now, when we're talking about reactions, as we'll talk about, right, when we talk about a reaction where we have reactants that go to products, our final state is pretty much our products, right? Our initial state there is our reactants. So a lot of ways that we calculate thermodynamic sort of properties is to take products minus reactants, which gives us basically where we ended versus where we started in terms of like energy and so forth. So if you end in energy, higher than where you started in terms of your reactants, you may have like an endothermic process where you actually absorbed energy overall. Vice versa, if you ended lower in energy of your products than where your reactant started, then you'd have more like an exothermic reaction where energy was sort of released. Any questions on that there? So when we talk about energy, there are several types of units that are commonly we come across here. There's a bunch of them. None of these are negative, by the way. That's just from PowerPoint, so scratch all that out there. So the SI unit there, SI, throwback name. The SI unit there is a Newton meter, which we never use here, but we use a kilogram meter squared second squared. And more commonly, units of energy are joules and kilojoules are very common units of energy, along with calories and kilocalories as well. These are two very common sort of units of energy. This relationship does pop up, and maybe you saw it probably last semester. 1 joule is equal to 1 kilogram meter squared second squared. So that is a conversion that sometimes does pop up. There obviously is 1,000 joules in a kilojoule. A calorie, which in this case is a lowercase c calorie, is basically the amount of energy required to raise 1 gram of water by 1 degree Celsius. So that's sort of a definition of a calorie. And an important sort of conversion between calories and joules is this one, which is 4.184 joules is equal to a calorie. That is also, as we will see, and maybe you remember from, since they don't teach it last semester, we'll have 100. That is also the specific heat of liquid water, 4.184 joules per gram per degree Celsius. One way that we use energy is to change the temperature of a substance. Again, ice to liquid water obviously requires some energy being inputted to do that. The ice cube needs to pick up energy, and that's also, as we'll talk about in a later chapter, it's also a spontaneous process, right? If you take an ice cube out, it will just start melting by itself, right? And it'll pick up all that heat and energy from the surrounding air, and it will start the melting process at that point. Some other sort of units of energy. There's also, in terms of calories, there's also a capital calorie with a capital C. That is sometimes referred to as a nutritional calorie, and that is equal to 1,000 of the little c calories, and that also equals 1 kilocalorie. So a capital C is more of a nutritional calorie, like calories you ate, calories you exercised off, all those type of things. And that is 1,000 of the little c. So there is a difference if you capitalize C per calorie versus non-capitalization of the C. And again, in most cases, we deal with usually the smaller c, unless you're doing something with nutrition as well. Now, thermal energy is the energy associated with the random motion of atoms and molecules. And thermal energy is based on really how many particles, atoms, molecules you got there. The more atoms, molecules, and stuff in the substance, the more thermal energy you're going to have, because there's going to be a lot more people moving around, vibrating and bouncing around and motion and all that kind of stuff. And that's going to cause a lot more thermal energy. Again, thermal energy is different than temperature. Temperature is sort of a measure of the energy change that occurs within a substance. And to sort of illustrate the distinction between thermal energy and temperature, if we took, for example, a cup of coffee that is at 70 degrees Celsius, and we took a bathtub here of water that's at 40 degrees Celsius. The bathtub of water has a lot more thermal energy than the cup of coffee there, even though the cup of coffee has a higher temperature as well. And again, that's because the bathtub there obviously has a lot more water molecules in it than your cup of coffee, I hope. Otherwise, you're drinking too big of a cup of coffee. But the temperature difference is also a difference that you see there. The reason for that has something to do with what we'll talk about in this class as well, in this chapter, the specific heat capacity, for example, of liquid water. There's a lot less liquid water there in the coffee cup, which means you don't have to put as much energy in there to see a bigger degree difference in terms of the temperature. You would have to heat that bathtub up a lot there to put a lot of energy in there to get it up to 70 degrees. It's kind of like when you boil water to make pasta, you put water in the big pot. It takes a while for it to boil, right? Put a small little pot of water up there with not a lot of water in there, it's going to start to boil a lot quicker, right? So it takes a lot more energy input to change the temperature of a big amount of water than it does, say, a small amount of water to do so. That's why people get worried about the ocean, right? When it goes up just a small amount of temperature degree, right? Think about how much water is in the ocean. Just to move it that much of a temperature degree takes a lot of energy to do so, as the specific heat of water is pretty high. Any questions on that there? So when we talk about heat, heat is defined as the flow of energy due to a temperature difference. Heat always flows from the hotter object to the colder object, and that is always a transfer of heat. And when we have a process that is exothermic, that is when heat and energy is released from, for example, the system to the surroundings. And that is sort of a release of energy, which is exothermic. If we lit a match, if we lit a Bunsen burner, you could put your hands carefully near the fire there, and you can feel the heat coming off of it, right, being released to the surroundings. In an endothermic process, heat and energy is being absorbed by the system. And that, for example, is like our ice cube, right? We take our ice cube, as we just talked about, you take it out, it picks up all that heat and energy, because at that moment, the ice cube is a lower temperature than the surrounding air, right? Which is a higher temperature. And that's going to mean the air is going to transfer its heat to the colder ice cube and going to cause it to start to melt. That's also why when you make ice cubes and you put water in a tray like you used to do years ago and put those into the freezer to freeze it to make ice cubes, That is when you put your room temperature water into the freezer. The freezer's temperature is colder than the room temperature water, so the water loses all its energy to the surrounding temperature, and that freezes your water right into your ice cubes in that case. So again, heat always flows from hot to cold. Endothermic and exothermic processes are a lot of what we deal with in terms of really the first law of thermodynamics, which is all about really energy. These are some energy diagrams, and they represent both a exothermic reaction and an endothermic reaction. And when we look at these energy diagrams, there's some important parts. First off, here we have our reactants going to our products here. And the first thing that we see is we basically have a difference in energy of our reactants to our products. And if you take that difference in energy from where the products end to where the reactants start, this is what is referred to as we'll talk about a little bit later on here in this chapter, the delta H of this reaction, which is the change in enthalpy. That is a fancy way of saying how much energy is either gained or released in a chemical reaction, basically, is the delta H value. The way that we calculate, for example, the delta H, or one of the ways you could calculate the delta H of a reaction, is you take the delta H of your products, again, your final state, minus the delta H of your reactants, which is your initial state. And if we look at this situation here, my products are lower in energy than my reactants, which are higher in energy. So that's a lower number minus I guess we'll go with a larger number. So that would be more of a small number, I guess is the way to do that. Small minus a large number, right, will get you a negative value. So if you have a delta H that is negative, that is going to tell you it's a exothermic reaction because your products overall in energy actually ended up lower in energy than where the reactant started. The only way that happens is you have to give off energy in that reaction. And that is your definition of an exothermic reaction. Now, that is different than what we see over here in an endothermic reaction. This is our reactants over here. This is our products over here. And the difference between the reactants, again, if I could draw a straight line, and the products here is going to be our delta H of this reaction. And when we think about what's going on in this one, our products, which is our final state, is actually a larger value than our reactants, which is a smaller value or a lower value of energy. That's going to yield you a positive value for the delta H in an endothermic reaction. You could also think about the only way the reactants can get up there in terms of energy needs to go in or be absorbed basically as a result of this reaction. That is probably the most common way in chemistry that you know whether or not the reaction is exothermic or endothermic. It is based again on that sign that happens. So what happens in a chemical reaction, as you hopefully know, the only thing that happens is bonds break and we make new ones, right? So we break all the bonds of our reactants and then they reform new bonds on the other side to make our products. And that is actually happening as it goes from reactants to products here, as it's going up this hill, as it is climbing this hill to get to the very top. This hill from the reactants to the very peak of the hill, this is what is known as the activation energy, or the E of A. That is the activation energy. It is the minimum amount of energy that's required for a reaction to take place. And if we look over here on our endothermic reaction, this right here is our activation energy. To the top of this hill right here is our E of A as well. When we get to the very top of the hill of this sort of energy curve, we are pretty much at the highest point in energy, which would be right about there and right about there. This sort of highest point of energy is what is referred to as the transition state. And that would also be obviously a transition state right there. And that's the highest point of energy in terms of this reaction that's occurring. One thing that we hopefully know is, are things in chemistry more stable or less stable if they're high in energy? Less stable, right? The whole point of pretty much everything is to get everybody kind of in the lowest energy possible. So this is really your highest point along the way in a chemical reaction. It's the highest in energy. And what happens is you actually have something up here, which is sometimes has like a little symbol like that, like a transition state sort of symbol. This guy at the very top of the hill is what is referred to as the transition state complex, or sometimes referred to as an activated complex. And basically what that thing is really your transition between reactants and products. So as these reactants are climbing up this hill, what is starting to happen is all the reactants are starting to break their bonds. So they're partially starting to break away their bonds. At the same time, they're actually starting to make their new bonds. So this is really sort of, I'm partially breaking some of my old bonds, and I'm also starting to make some of my new bonds along the way. And when we get to the very, very top, that is why we get this transition state complex. We got a guy that basically has partially made bonds and also some partially broken bonds, which is why it is also very, very unstable. It doesn't hang around for a very, very long time. A lot of reactions, it's very hard to, for example, try to isolate that guy in the middle point there because it's so high in energy, it's so unstable. It doesn't hang around a very long time. And what typically happens is it will kind of drop down the hill relatively quickly to get to the other side. At that point, again, we have that sort of exchange in energy, which either results in an endothermic process or an exothermic process. Any questions on that there? Yeah.
Yeah, I see. What at the transition state, like what is the downslip?
Yeah, so this is more for a chemical reaction, what we're looking at here, right? That's more of a physical change, right? The melting of the ice and stuff like that. What happens sort of in between those two is actually you have a little bit of both actually happening. It's kind of like what happens at the transition state. We got partially made bonds, partially broken bonds. Where that happens is like at 0 degrees Celsius, for example. At 0 degrees Celsius, you got like liquid water and also ice at the same time, like ice crystals. So you got a little bit of everybody in equilibrium with each other sort of occurring at that point. So it's kind of similar to what happens in chemical reactions where you got at that kind of height of energy where it's going to kind of come to the products. You got like partially broken bonds, partially made bonds. You got everybody kind of together at that point. Now, when we do have a chemical reaction, there is one way that we can sometimes speed up a chemical reaction, as you may remember. So we got a little go this way, our reactants and our products, right? And this is our activation energy, right? Now we could add a catalyst, right? And a catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. Really, the point of most of the time when you add a catalyst is to speed up the chemical reaction. It does that by finding a more efficient pathway for that reaction to take place. And ultimately, by finding that sort of more efficient pathway for that reaction to take place, what happens in terms of our diagram here is in a catalyzed reaction, we typically are able to lower the activation energy by finding that more efficient pathway of doing so. What that essentially does is, right, the idea here of the activation energy is it's the energy barrier to allow a reaction to take place. And there's only a certain amount of reactants that have sufficient amount of energy to get up and over the hill to the other side. So when you add a catalyst, what you're doing is lowering the hill. That's going to allow a greater proportion of reactants to get to the other side, and thus usually increases your rate of reaction. Like if you had to walk a giant hill to get to the other side of campus, or just had to go over like a speed bump, right? A lot of people get up and over the speed bump, right? A lot more people. And then maybe if they had to walk a giant hill to get to the other side. And that's the idea here of a catalyst and why it's able to sort of speed up the reaction. Also why, typically speaking, if you remember from kinetics, when you raise the temperature of a reaction by like 10 degrees Celsius, it usually will double the rate of the reaction for a lot of reactions. And because when you add more energy to your reaction or increase the temperature, your reactants now gain more energy, and there's a greater amount of reactants that have enough energy now to get up and over the hill, which is why your reaction would occur faster. Or if you put everybody on ice, you're going to see your reaction probably slow down because now you have less amount of reactants that have enough energy to get up and over to the other side. Maybe you did that in that last kinetics experiment 200 a day. There was like a hot water bath and an ice bath versus the room temperature and how long it took to turn purple, blue, purple. One of those, blue or purple, I think. I don't remember. Because it's usually at the end of the semester and go, why are we doing this experiment? All right, so here's some other sort of energy diagrams, but again, here the formation of liquid water from hydrogen gas and oxygen gas is exothermic. It's going to release that energy to the surroundings. The decomposition here of mercury to oxide into mercury and oxygen is an endothermic reaction, also takes a little bit more energy to do so. As you can see, am I really badly drawn here? So I'm gonna get rid of all that. We could also see, just looking at our diagram here, which one has the greater activation energy. The endothermic reaction, right? Which is why it's probably endothermic. It needs a little help to get everybody kind of up and over the hill versus obviously the guy on the left there, which actually has an excess amount of energy. You want to think about that way, that can release it as it's going through there. Also, the activation energy determines, again, how fast or slow that reaction takes place. A bigger activation energy, a slower reaction usually. So when we talk about exothermic and endothermic reactions, we also talk about it in terms of, is energy sort of a reactant or product? We sort of talked about that when we did Le Chatelier's principle. We talked about temperature. And typically speaking, when we think about an exothermic reaction, we think of heat and energy as a product, like it is being given off, like in the chemical reaction. And when we talk about an endothermic reaction, we think of heat and energy as being a reactant, like it's being absorbed. So here, as we talked about before, if you have some water at some different temperatures here in this isolated container, insulated container, heat is going to flow this way. When it does so, all the water molecules in here are going to gain some energy, start moving around a lot faster. The result of that is we're going to see the temperature start to rise on this side. When this side loses the energy, everybody's going to slow down a little bit, and we will start to see the temperature decrease here on the left as that transfer of energy is going. That is really what we can use temperature to measure, right? Is sort of the transfer of energy. If we see the temperature increase, then that substance obviously gains some energy to do that. If you see the temperature of something go away or lower down, then obviously that thing is releasing the energy, right? In that case. Now, again, eventually what will happen here is, they'll kind of equal out there probably about halfway between their temperatures there at 50 degrees. They'll come basically to equilibrium with each other, right? In terms of their temperature, as that energy will be transferred enough that everybody will end up at the same temperature. Now, enthalpy, as I mentioned before, is really the measure of how much heat or energy is released in a chemical reaction. It probably is the most common sort of way that we express energy. And enthalpy is oftentimes calculated as the delta H. And as I mentioned before, very common way that we do this is to calculate and add up all the delta H values of our products minus the delta H value of our reactants. And again, really the number doesn't matter all that much in terms of exothermic or endothermic. What does matter is the sign. So again, if you see a negative sign for delta H, you know it's exothermic. And if you see a positive sign, you know that it is endothermic in this case. There is a table where you would look up these values known as the delta H of formation table, and you would look them up based on the substance. It's also really important when you would do so that you make sure you get the substance you're looking for, but you also make sure that you do get it in the correct state. And I say water is a very common one that people mess up on. They just find the first H2O they see in the table. It might not be the right state that you need. So you do want to make sure it's not just the substance, but whatever the state may be as a solid, aqueous, gas, whatever it may be. So here are some values of delta H of formation from a table. So why don't you calculate that? And by the way, before we do that, let's just talk about more so maybe how to do that. That would be good. But like there would be another slide there, but there wasn't. So for example, if we had this reaction of 2A plus B goes to 4C, and we want to calculate the delta H of this reaction. Basically, we would go to this table of our delta H of formations, and we just make up some here. So A will be 20 kilojoules, B will be -4 kilojoules, and C will be, why not, 15 kilojoules, why not? Now, when we go to calculate this, it is also important that you take into account the coefficients in the equation when you're calculating these, and it does matter in this case. So if we were to calculate this, we would do our products minus our reactants. And basically what we would do in this case is take our delta H of our reaction. We'll start on our product side. There are 4 C's. We would take 4 times the value of C, which typically this is kilojoules per mole. And we'll take 15 kilojoules there. That is all of our products, basically. This is basically moles and times moles here. We're going to then subtract it from all of our reactants. So there are 2 A's. So we do have to take 2 times the value of A we find in there, which is 20 kilojoules per mole. I'll put it in here per mole. And we then need to add it to our other reactant, which is B. And in this case, that is going to be 15 kilojoules per mole. Technically speaking, we would be multiplying this by 1, which we don't really need to do, but technically we'd be multiplying by 1, which is the coefficient here. We would add all those together and subtract. So we'll take 4 times, what did I do there? 15 minus we got 2 times 20 plus 15. I feel like I did 15 twice there. I feel like I did. And A was 20 and B was -4. That was like way, way wrong there. Hey, I'm still on spring break. Let me know. All right, so let's get the right number for my bad made up table there and actually put the right number in there. So that's going to be actually B, which is 1 here. So that's going to be -4 kilojoules. There we go. Let's try that there. All right. So we got -4 in this case. There you go. That's going to give me 24, I think, in this case. I hope. For my delta H of this reaction. This reaction would be exothermic or endothermic. This would be endothermic, as it is a positive value here for delta H. So you do have to take into account the coefficients. You got to multiply them by the values that you find in the table. By the way, delta H is a formation for things in their standard states are going to be 0 kilojoules, like O2, H2, N2, anything uncombined kind of by itself will have a delta H value of 0 in those tables if you look them up. All right, now let's try a roll in here, maybe. That's right. There you go. All right, so those are the values you find from the table. Calculate the delta H for this reaction here. Entropy is chapter 16. Coming up next. Entropy is the delta S is the amount of randomness or disorder there is in the universe. Also known as the next chapter we'll get to the rest of it. All right, so let's take a look at this one. So again, in this situation, if you're asked for the delta H of the reaction, and that's all you're given is the equation, pretty much you're going to go and look it up in the thermodynamic table, which is probably found in most books in the back. And we're going to do basically our delta H of our reaction. Again, we're just going to add up all of our delta H's of our products and subtract it from basically your delta H of our reactants. I'm going to try to do better than I did last time here. Let's see. We'll go with our product side here. So we have two NaOHs at minus 470. We have an H2, and as I mentioned before, these are typically going to be 0 type values that you find. That takes care of basically of all of our products, really our final state. Now we're going to do all of our reactants, our initial state. So we have 2 times our sodium, which is also in the standard state, which is going to be 0. Plus our 2 times our water in our liquid state, which is minus 286 kilojoules here. And this is our reactants, our initial state, right? So if we do that there, 2 times minus 470 minus 2 times negative 286. Going to get us a delta H here of about negative 368 kilojoules. This would be endothermic or exothermic. It is exothermic as we have a negative value for delta H. Any questions on that one there? All right, let's try a couple more here. Good talk. Let's make it bigger, maybe. I don't know. It looks small. Get it before it moves off the screen. All right, calculate delta H here of this guy. On the product side, we got 16 of the carbon monoxides, each at 110. We're going to add it to our other one there, which is 18 of our waters, times our water there, which is minus 286 kilojoules. That's going to take care of all my products here. We're then going to subtract it from our reactants. So we got 2 times our C818 there. So that's 2 times minus 208. We're going to add that to 25 times a 0 there for our oxygen. That's going to take care of our reactants there. And that will get us here 16 times negative 110 plus 18 times negative 286 minus 2 times negative 208. And give us, I think, a negative 6492 kilojoules in this case. Yeah. Any questions on that one? Again, here, this is going to be exothermic as well, as we have a negative delta H, and since it's a combustion reaction, probably would make sense, I imagine. All right. One last one here, I think. Okay, so once again here, you would go to the table if it wasn't provided for you, and we'll do our, again, products minus our reactants. So 12 times our CO2 value of minus 393.5. We're going to add that to 6 times our water, minus 286 kilojoules there. That is going to basically take care of all of our products here. I'll do underneath here our reactants. So minus our reactants, which is 2 times 4904. plus 15 times a 0 for all of our O2. That's going to get us here negative, it looks like we'll call it 6536 kilojoules in this case. Any questions on how to calculate delta H here? So again, just an equation, go to the table, look it up, make sure you take into account the coefficients there. Any questions on that one there? All right, so let's try this one here. Consider the combustion of propane, which is C3H8. It gives this reaction a delta H overall of minus 22. I'll get that right. A lot of T's and a 1 there. Assume that all the heat comes from the combustion of propane. We want to calculate the delta H when 0.113 moles of propane is burned in excess oxygen. So sometimes you are given an equation here with the delta H value. And you actually can use the equation kind of like in stoichiometry, where you kind of do a mole to mole relationship. You could actually use the equation with like a mole to energy relationship that you see to maybe answer a question. So, for example, in this one particular case, we want to know basically how much energy is required when we do 0.113 moles of propane, which is C3H8. Now, when we look at this reaction, this is propane here, and these are our coefficients, right? So basically, we have 1 mole of propane in this case, and 1 mole of propane will actually produce, in this case, negative 2221 kilojoules of energy. And we could use it just like a kind of stoichiometry conversion factor. You could kind of write it like this over the energy value. Or you could flip it around and kind of put the energy value up on top over 1 mole of C3H8 as I try to squeeze it in there. Now, in this case, we want the energy for 0.113 moles, and that should hopefully be less, I would imagine, than 1 mole that we have here. So we could actually just do a little calculation, 0.113 moles of the propane. We'll use our conversion factor, opposites cancel, so we'll use this one here on the right, minus 2221 kilojoules, and that is 1 mole of propane here. These guys are going to cancel, so we'll basically take 0.113 times minus 2221, and that's going to give us minus 251 kilojoules of energy, which is less than the 1 mole that gave us basically 2200 kilojoules of energy. So you could actually use an equation and the energy, sometimes referred to as thermochemical equations, and basically get a conversion factor that ties in energy to the moles of everybody in there. You could also do it for like anybody else really in the reaction as well, like O2. It would be 5 moles of O2, right? In this case, would produce you that same amount of energy. So that is another sort of aspect of delta H. Use the equation as a conversion factor that gives you moles and energy associated with it. Just like obviously if I wanted to know, how much energy in 2 moles of propane, I basically would just say 2 times that, right? It'd be the same calculation, just start with 2, and then we'll get double the amount of energy, which again is what you would probably expect to occur in this case. Question on that there. All right, then let's talk about specific heat and specific heat capacity. Good talk. Again, this is not negative, just from PowerPoint there. All right, specific heat capacity is actually the pretty much same definition as a calorie definition, except it's more generic. So specific heat capacity is actually the amount of heat or energy that's required to raise 1 gram of whatever substance you're dealing with by 1 degree Celsius. There is a specific heat equation that maybe you remember is Q is equal to ms delta T. Q is heat or energy. M is mass. S is the specific heat capacity. And delta T is the change in temperature. Now, I will say that some books and some people will use some different values or letters for specific heat capacity. Commonly, sometimes people will use C for specific heat capacity. Some people use SH for specific heat capacity. I roll with S because I don't know, probably it was beat in my head at some point along the way and I can't get it out. So sometimes people use some different sort of letters to represent the specific heat capacity. Now, in terms of these guys here, we want to watch out in terms of units of what we need going on. So Q is heat or energy, and that is typically units of joules or calories are your two sort of common units for Q. M is mass, which is units of grams typically. S is the specific heat capacity, and that is the one that actually has 3 units associated with it. That is joules per gram per degree Celsius, or if you're working the calories route, calories per gram per degree Celsius. And change in temperature is probably one of the few chemistry equations or formulas that, surprisingly enough, you don't need to convert to Kelvin. This is usually in degrees Celsius. And that is because our specific heat capacities are usually in degrees Celsius. So everything cancels out. So it's kind of one of the few ones. But super important when you do the change in temperature is this right here. The change in temperature is the final temperature minus the initial temperature. And you should always do that. Sometimes people are taught, I won't say incorrectly, but maybe they're taught not so right, that you could just take the difference of the temperature and everything's good. And you don't want to do that. And I'll explain to you why you don't want to do that in just a second. As soon as I take a drink here of water, by the way, for the recording. And it has to do with really the sign of Q. So when we calculate Q, if Q is negative, that means that typically is going to be an exothermic reaction that's going to take place. And if you calculate Q and it's positive, it means it's an endothermic reaction. Typically, most energy values, if it's negative, means it's going to be exothermic, and if it's positive, it's going to be basically endothermic. So why this is really important is if you just look at this equation, let me zoom in on there so you could really look at it there. This number here, mass, is going to be positive. Specific heat capacities are positive, which means really the only thing that could be either positive or negative are what really determines whether or not the reaction is going to kind of be exothermic or endothermic is the change in temperature. So if you do one where you do get a negative number, that's what's going to turn your Q into a negative value and tell you it's exothermic. And if you do the change in temperature and it's a positive change, then it's going to tell you it's an endothermic reaction. So it's really important to do that. And again, Q can be negative or positive, and it's based on the temperature. So as we talked about last time, if somebody's final temperature minus the initial temperature, if it started out at a high temperature or finished at a high temperature and started out at a small temperature or a lower temperature, that difference is going to get you a positive value, right, for change in temperature and a positive Q. Because really the only way to do that is if your temperature is here and it gains energy, temperature is going to rise, right? So you're going to end up at a higher temperature than you started with. Now, if your final temperature minus your initial temperature is the opposite, you end up with a, I guess you should do right words there, a lower temperature versus the higher temperature you started with. You're up here, and the only way for that to happen is you have to lose energy for your temperature basically to drop, which means that will give you a negative for the delta T, and that will give you a negative for the Q, which means it's exothermic happening. So that sign of Q is really important, and you should keep the negative on it if you do calculate a negative value for energy, because it does indicate to people whether or not the reaction is exothermic or endothermic as to whether or not there is again, a negative or positive sign on your value. The other thing that's very common that people screw up on this equation is they like to confuse these two guys together. So Q only has one unit and S has all three. So people always want to kind of swap those guys together. By the way, the specific heat capacity of liquid water, which is what that number is down there, it's actually liquid water, is 4.184 joules per gram per degree Celsius. Or if you're doing calories, it's 1 calorie per gram per degree Celsius. That is, as we saw earlier, the conversion, right, between calories and joules, where 1 calorie is 4.184 joules in this case. That is the definition, by the way, of specific heat capacity. The definition, as I read it to you, is the amount of energy, joules, in 1 gram of a substance to raise it by 1 degree Celsius. So that is the definition and why it has all three of those units associated with it. Any questions on that there? If I have a really large value, or if I have a large value specific heat capacity, does it take less or more energy to raise the temperature by 1 degree Celsius? Takes more, right? If you have a small specific heat capacity, it doesn't take as much energy to see a big temperature change. So that goes back to what I was saying earlier about the ocean and the temperature change that occurs there. Liquid water has a fairly significant specific heat capacity. It takes a lot of energy just to move up the temperature a tick of 1 degree Celsius. And when it goes up just a very small amount of temperature, it takes an enormous amount of energy just to move that much water, that little bit of temperature along the way. That is also why if you go back to our bathtub example and our cup of coffee example, that is why our cup of coffee could get to 70 degrees a lot easier than our bathtub of water. There's a lot more water molecules in there. It's going to take a lot more energy basically to get that guy to move that much of a degrees in terms of temperature. Here is a table, and as you could also see, water in the ice version is actually 2.03 joules per gram per degree Celsius. In the steam version, it's actually 2. So it's important as well if you're doing a calculation, for example, with water, that you know, is it liquid water, is it steam, or is it ice? Because they will have different specific heat capacity values when you do that. So here you can see gold is relatively small specific heat capacity versus, again, our water, which is a relatively high specific heat capacity. All right, so why don't you try one here? Determine the amount of energy as heat required to raise the temperature of 10 grams of aluminum, specific heat capacity 0.89 joules per gram per degree Celsius, 25 to 58. Give the answer in joules and calories. Heat is Q. We have definitely a mass there of 10 grams. We have a specific heat capacity given to us of 0.89 joules per gram per degree Celsius. And we have an initial temperature here, 25 degrees Celsius, and a final temperature of 58 degrees Celsius. So using our equation here, Q is equal to ms delta T. Just got to plug in. So we're going to go 10 grams times our 0.89 joules per gram per degree Celsius. Again, we're going to go final temperature here minus initial. And that's going to get us here. About 293.7 degrees Celsius cancel, grams cancel, leaves us joules left over. And we still care about sig figs at this point, 290 joules maybe as we go through there. Now we do want it in calories as well. So here we have 1 calorie is 4.184 joules. So we'll use our rounded number, maybe, I don't know, I guess so. We'll go 4.184 joules per calorie in this case. Joules are going to cancel. I guess I should use a rounded number on my calculator there. I'll go 69 calories in this particular case. This is a endothermic process, right? And we know that as well because here we see our temperature actually rise, right? Our temperature went up from 25 to 58. The only way that could happen is if it gains some energy to cause the temperature basically to increase in this case. Any questions on that?